Hi Year 10. This is the first in a series of 5 videos for the topic of non-right-angled trigonometry. In this first video, we're going to look at three-dimensional trig. So here's the lesson outline. We're going to start by reviewing what you learnt in Year 9, including SOHCAHTOA, angles of elevation and depression and bearings, and then we'll have a look at how we apply right-angled trig in 3 dimensions. So recall that there are 3 trigonometric ratios that we can use to solve problems. There's sine, cosine, and tangent. And also remember, when we're labeling a right-angled triangle, the side opposite the right angle is called the hypotenuse. And then in relation to the angle, the side opposite the angle is called the opposite side, and the side next to the angle is called the adjacent side. Now we define sine theta as opposite over hypotenuse, cos theta as adjacent over hypotenuse, and tan theta as opposite over adjacent. And we can tie it all up in SOHCAHTOA, which stands for sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent. Let's look at some examples. Triangle ABC has a right angle at B. Angle BCA is 23 degrees and side BC is 14 meters. Find the length of side AB. And sometimes you have to draw your own diagram. So we'll start with a right-angled triangle. It's right-angled at B. A and C, it doesn't really matter which way around they go. Now we know that angle BCA is 23 degrees, side BC is 14 meters, and we want to find the length of side AB. All right, now we've got to figure out which trig ratio we want to use. So we'll start by labeling the sides. Opposite the right angle is a hypotenuse, and there's nothing on the hypotenuse. Now let's locate the angle. It's here. Opposite the angle is the opposite side. Next to the angle is the adjacent side. So looking at SOHCAHTOA, we want tan, don't we? We've got opposite and adjacent. Now this works like a little formula. It says that tan of the angle is equal to opposite over adjacent. So tan 23 is equal to x over 14. And we're going to take our 14 over the other side. Multiply by 14. X is equal to 14 times tan 23. Put it in the calculator and we get 5.94 meters. Example 2. Find the length of the hypotenuse in this triangle. So let's start the same way. We'll label the sides of the triangle. Opposite the right angle is the hypotenuse. Locate the angle. Opposite the angle is the opposite side. So we have O and H, which is sine. Sine 33 degrees 14 minutes is equal to 19 over x. You can see how we've ended up with the pronumeral on the denominator. Now a really quick trick is just to switch these two, but we should find out why that is. So we're going to do it the long way first. We're going to start by timesing both sides by x. They cancel. And then I'm going to divide both sides by sine 33 degrees 14 minutes. And these cancel. And I end up with x is equal to 19 over sine 33 degrees 14 minutes. Now let me just rub all of that out for you and have a look what's happened. Can you see that the x and the sine 33 degrees 14 minutes have switched places? So anytime you end up with the x on the denominator, you can just switcheroo. Now we need to put that in the calculator, and we've got an added layer of complexity here because we've got degrees and minutes. And on your calculator you want the degrees, minutes, seconds button. I affectionately call this the bubble button because it looks like bubbles. So you can use your fraction button if you want to, and then type 19 in on the numerator, and then sine 33, hit the bubble button, 14, hit the bubble button again. If you don't hit it the second time, you'll get an error. But when you press equals, you'll end up with 34.7 centimeters. And example 3. This time we're going to find an unknown angle, but we're going to do it exactly the same way. Let's start by labeling the sides. Opposite the right angle is the hypotenuse. This is the opposite side. This is the adjacent side. And looking at SOHCAHTOA, we have opposite and adjacent, we have tan. So tan alpha will equal 7 over 16. Now I want to make alpha the subject, so I'm going to take the tan over the other side, and the opposite operation of tan is inverse tan. So alpha is equal to inverse tan of 7 over 16. Now on your calculator you will do shift tan. And when we do that we'll end up with this. But we want the nearest minute, so we're going to press the bubble button and we get this. Now this is degrees, minutes, seconds, so we want to chop it off here. But here's the thing, because degrees and minutes are out of 60, we're going to round up over 30, and that 45, that's more than 30. So our answer is going to be 23 degrees, 38 minutes. Now another thing you covered in Year 9 is bearings. And recall, a true bearing is the rotation from north in a clockwise direction. So we would say that the bearing of S from P is 125 degrees true. Now in a question, locate the word from, and whatever comes after that, that's where your compass goes. Here's an example. A ship travels from Port P on a bearing of 312 degrees for 12 kilometres. Then it turns and sails east until it is due north of P. How far did it sail east? So we need to start with a diagram. Here's a compass. Port P is at the centre and this is north. Now we're sailing on a bearing of 312 degrees. So from north in a clockwise direction, that takes us around into this quadrant. So 12 kilometres we travel on a bearing of 312 degrees. Then the ship turns and sails east until it is due north of P. How far did it sail east? So we want to work out this distance here. Now we need an angle in the triangle, but that's pretty easy because a revolution is 360. So we're going to take off the 312 and that will give us 48 degrees. So let's tidy this up. And now let's do some trigonometry. We have got opposite and hypotenuse, which is sine. So sine 48 is equal to x on 12. Multiply both sides by 12. And in the calculator, the ship has sailed 8.9 kilometres. Now, living in a three-dimensional world, there are lots of opportunities to use trigonometry to solve problems. Let's start with a nice simple one. Here we have a rectangular prism. We know the length is 10, the width or breadth is 4, but we don't know the height. However, we know that this diagonal AC makes an angle of 30 degrees with the horizontal, or the length here. So let's use that information to find the length of BC, which is the height of the prism. All right, in relation to this angle, this side is opposite and this side is adjacent, so we're going to use tan. Tan 30 is BC over 10. Multiply both sides by 10, and BC is equal to 10 tan 30, which is 5.77 centimetres. Now let's use that information to find the size of angle DAE. So you can see how this particular angle is going across through the middle almost of that prism. So let's draw that in. Okay, so we want this angle in here, and we'll call it theta. All right, this is a right angle here, so we're going to have opposite over, well actually we don't have either of these sides. But if we have a look at the base of this prism, we can use Pythagoras' theorem on it to work out what AE is, because this is also a right angle. So we'll start there. AE squared is equal to 10 squared plus 4 squared, which is 116. AE is equal to 10.77 centimetres. And now we're ready to use trigonometry to find this angle. Again, we have tan, opposite over adjacent. So tan theta is equal to 5.77 over 10.77, which is 0.536. Inverse tan of that gives us 28 degrees. So theta is 28 degrees to the nearest degree. We can also use trigonometry in real life to calculate heights of buildings or widths of river. And we don't need to cross the river in this case. So if we use our instruments, say we line up a tree on the opposite side of the river, and we stand here perpendicular to the river, and then measure a distance along the bank, and then use some instruments to work out the angle between this first post where we were standing and the tree, then we have enough information to calculate the width of the river. In this case, we're going to use tan, and tan 32 is W over 15. Multiply both sides by 15, and we get 9.4 meters. Now recall that the angle of elevation is the angle from the horizontal up to an object, and the angle of depression is the angle between the horizontal down to the object. Now you might also remember that the angle of depression and the angle of elevation are actually the same size, and that's because they are alternate angles on parallel lines. And this can be really useful because more often than not, the angle of depression is outside the triangle. So here's another real-life example. This time we're going to work out the height of a building. A man sits across the road from a tall building. He measures the angle of elevation from the ground to the top of the building as 23 degrees. If the distance between himself and the bottom of the building is 110 meters, how tall is the building? So again, we're going to need a diagram. So here we have a building of unknown height. We know the angle of elevation is 23 degrees, and the distance between the bottom of the building and the man is 110 meters. So we have opposite and adjacent. We have tan again. And it's not unusual in real life situations because we're not often working out the length of the hypotenuse. So don't be surprised if tan turns up. Multiply both sides by 110. X is equal to 110 tan 23. The building is 47 meters tall. Let's try one more example. Two identical buildings with dimensions 10 meters by 5 meters by 18 meters are 7 meters apart as shown in the diagram. Find the angle of depression from point A to point B. Okay, so these buildings are always 7 meters apart. They're parallel to one another. Now, if we want to find this angle of depression from A to B, we're going to need to know this diagonal distance between the bases of these buildings. So I'm going to start by labeling the point below A as C. Now we need to calculate BC, and we're going to use Pythagoras' theorem. We know this distance here is 10 meters. So BC squared will equal 7 squared plus 10 squared, which is 149, and BC is equal to 12.21 meters. Now let's try and draw this triangle here. So from AC to B. And this looks a bit like that, doesn't it? So we've got 18 meters is the height of AC, and we worked out that BC was 12.21 along here. Now we want the angle of depression. So that's here. But remember that we can use the angle of elevation instead because they are alternate. So let's draw a little theta down in here. And it's going to be tan, isn't it? So tan theta will equal 18 over 12.21. Inverse tan of that fraction, and we end up with 56 degrees to the nearest degree. Okay, that's the end of this lesson. In our next lesson, we're going to start looking at the formulas that we can use for non-right-angled triangles, and the first one is the sine rule.